So now, going to the ISA in the remaining 15 minutes. So to understand the mindset of coming up with this ISA contract, we have to understand that all modern architecture, at least the general purpose computing ones, they follow what we call the 191 model. This ones means you follow the control path of your program, not the data flow path, right? And in reality, this is one of the big decisions in computer architecture that is also currently being disrupted a little bit because of machine learning. So it's important to understand that concept. We said last week that for your processor organization, you have two main components, or two main paths you need to do: control and data. And we said control is the one that is responsible for fetching instructions from the memory and then decoding it, understanding what operation you want to do, and then feeding the control lines, the selection lines of the multiplexers, the enables of the ALUs, and all these control lines to the actual functional units to stimulate, to start the operation. The actual operation and the data transfer is happening through the data path. To read the two operands, so let's take add instruction as an example. I have add one, R1, R2, R3. First, this is encoded in the memory as a binary, right? I fetch it from the memory as a control unit. So this is control, you do the fetch. Then you have to decode it to understand this is an add and what are the operands, right? And then after you decode it, you enable the hardware machine, the function units, to do the actual addition. The actual addition and the transfer of R1 and R2, so you need to bring in, there is something called register file, and we have the ALU here. R1 and R2 are stored here. You need to read these two, do the addition, store it back to R3, right? This type of reading from the register file, executing the ALU, and then writing it back, this is the function of the data path, right? The data path is the one based on the control unit. It knows what to do, and then it executes it. So the actual execution and then writing back and reading from the register file is done through the data path, right? All the modern computing machines, at least the ones that are general purpose, are designed based on the control path and not based on the data path, right? So what controls it is, what are the steps do I follow is in fact determined by the control path. So the control path is the active unit. While the data path takes the selection, the enables, it's the actual, the one, it's basically the one that is executing the instructions that comes from the decode unit, right? Why I'm emphasizing this? Because there is a completely different type of machines. It's called the data flow machines, right? Data flow machines is like, for example, how do you write RTL for an FPGA? Again, I will take 3DQ as an example. You design your function units around the data, not around the control, not around the execution. Like, for example, if I tell you, well, you have to design a search algorithm, you start saying, I'm not sure you covered this a lot in 3DQ or not, but I hope yes. You start saying, okay, how many multipliers do I need? Well, this will really depend on what operations do I do. And then based on the data, I put registers here. And then the output will be in a register here. And then after these two registers, I multiply these two, and then add this one, and then come up with the last result, right? This is called the data flow diagram. Have you seen this before in any way? Yeah. So you start thinking about designing your hardware based on the data, not based on the control, not based on the type of the instructions you do, but based on, I simply need to add these two registers. So I need to add an adder here. And you start throwing adders and multipliers and function units everywhere around the registers, right? This is called data flow design. It's called data flow, but it's centered around data. On the other hand, for the control flow, you'll see that in all processors, we're talking about centralized hardware. There is an ALU function unit, branch prediction, everything in one place. And where is data? This is scattered everywhere. A register file, levels of caches, and main memory. And I start bringing in the data closer to the execution unit, do the execution, and then write it back, right? So you put the data close to the execution in the Van Neumann model or the control flow model, while you put the execution close to the data in the data flow diagram, right? In the past 40 years, all of our machines are basically control flow based. Recently, because there is a lot of bottlenecks of data transfer, there is a movement, especially again because of machine learning and AI and heavy data processing of autonomous systems, that, well, is data is the most expensive one, and its transfer is very expensive, as we'll see later on. Bringing some data from the main memory is a couple of hundreds of cycles, and add is just one cycle, 2 cycles. Why don't I put an ALU in front of the memory and then do the addition there and store it back quickly, right? So you start thinking more towards data flow. But that's not very well established yet. It's very specialized. If you have heard about TPU units, like tensor processing units, for example, from Google, or similar machine learning oriented chips from TensorTorrent and others, they are data flow. They're basically designing the hardware to optimize for data transfer, right? This is a philosophy completely different than what you have in your laptop, mobile phone, desktop, server, any general purpose computing machine, right? Good. So the one we're going to cover mostly here is, again, the control flow model, the von Neumann model. And then I'm hoping that I'm dedicating one lecture at the end to discuss the modern disruptions in computer architecture. Yeah. But it's more a topic for a graduate course than an undergraduate course. Great. So from that discussion, now I need to decide for every instruction what type of operations I do. And we said there are two main philosophies, RISC versus CISC. CISC, it basically says, well, how much effort you try to combine as much as you can the operations that one instruction can do. While in RISC, you just simplify it. You say, well, one instruction does one job at a time. Does anyone know which one appeared first, CISC or RISC? Yeah. Was it RISC? No, it CISC. But thanks for the answers. So basically, in very early days of computer, there were no compilers, right? You have to come up with programs your own that the machine is able to understand. Because there is no compilers, it's very hard to really write very long programs, right? As a human, writing a bunch of zeros or even instructions, it will be very long. I don't know if some of you try you don't have any labs that are Boolean assembly, right? But I remember in my undergrad, the embedded system course was Boolean assembly coding, right? For a very simple function that you now have in C in 2DX, you'd still be writing like a couple of hundreds of lines of assembly code, right? So if you write it yourself as a human, it's very, very tedious, right? From that pain, if you were trying to come up with an ISA that you generalize across machines, what will be your take? I want to minimize how many instructions I write, right? Because I write them my own. How do I minimize them? Put as many operations in one instruction as I can, right? You just simply the CISC thing, right? So the philosophy came from the fact that I want to simplify the programmer's life. Hardware is capable. Hardware we are able to modify early days, right? It's customizable. There is no compatibility issues, or not everyone is using the same hardware. So the hardware you can come up with a new design your own, right? So it wasn't very centralized back then that you need to stick to a certain hardware model. So there was no compatibility issues. So I can design it the way I wish. You simplify the programmer, the software side, and the hardware will serve you. And this is the philosophy of CISC. RISC came later on. And why did it come out? Well, once programming started being an interesting topic, people started to think of ways to make it easier. So they came up with this automation of translation from what you write to the machine code, which is basically compilers. And then programming languages start appearing, COBOL and like those very old ones, right? So in that case, now I have a standardized, easy way of write code, which is not really dependent at all on assembly. I'm no longer writing assembly. At the same time, there's a compiler that automates the translation process for me, which I'm not really worried of how many assembly instructions at the end will be in the program. On the other hand, designing the hardware became more complex. I want to simplify the design of the hardware because software became very easy at the moment. And here comes RISC. RISC is saying, I want to standardize what the hardware does. Every single instruction is doing one operation, which means once you get it from the memory, you know exactly what you need to do, right? And the instruction width is fixed, then you don't complicate your hardware design. And this makes the hardware way more efficient, standardized, easy to design and scale. And the software issue that originally was the main reason for the CISC is no longer there, right? We had compilers, high-level programming languages. Everyone was good, right? So this is why RISC came later on, and this is why RISC is in fact the winning philosophy, right? Because again, the pain is in the hardware, not in the software. Do you know what basically Intel does? Because they had to stick to CISC, right? Intel or AMD or whoever is using the x86, because we already came up with an ISA. I cannot break the contract. If I come, for example, in early 90s and say I throw away the CISC, and then I come up with a new RISC instruction set. I'm talking about Intel, for example, right? Then that means they are saying anyone that purchased their own processors in the past 5-10 years, obsolete. They cannot do this, right? So they have to maintain backward compatibility. So you have to stick to x86 instruction set. At the same time, it became very complex, and they are seeing that in fact RISC is winning in the performance battle because the hardware is scalable. You're able to design it better, efficiently. So what do? They keep the ISA CISC, but the hardware design is in fact following a RISC model, right? So what they do is they say, okay, this is ISA, the contract I expose to the software side. This is CISC x86. I cannot break. But whatever happens underneath is in my company, right? So I control this 100%. So they say, I'm going to accept your CISC complex instruction sets, but I'm going to add in the decode, usually in the front end of the processor, some translations that takes it from CISC and creates what they call the opcodes or the microcodes, which are simply just RISC instructions, right? So they do an internal translation to be able to scale the processor design afterwards, right? And this is how they are able to maintain good performance. In reality, CISC is just the exposed instruction set to the compiler. Underlying fundamentals of Intel processors and AMD processors right now, even if they're x86, they're in fact still following a RISC terminology, right? If you say, for example, x86 has a move instruction that is able to bring in things from the memory to, well, I'll just make it simple. So let's say I want to move this thing into a register, R2, right? What does this operation entail? Well, and this thing also might have an offset, which means you also need to calculate the operation, right? So you need to say, I have to go to R1 register, take the data there, use it as an address. This is what means square brackets, add 9 to it as an offset, take this full address, go to the memory, bring the data there, and put it in R2. This is what the move does, moving a memory location into a certain register. So assume a programmer wrote this, or the compiler gave you a move instruction as part of your assembly code. Then what the hardware will do is, well, if I'm following a RISC terminology or RISC philosophy, there is no instruction at all that deals with memory other than load and store. That's one of the design decisions of RISC, making it simple. If you want to deal with memory, it must be a load store operation, right? Any other instruction is only operating on registers. So for a RISC, I have to decouple this or decompose this into 2 instructions. So first I have to say load to one register, let's say it's R3, load this memory location, and then moving, you can say there is a move instruction that assembly takes R3 and put it into R2. Okay, so these 2 instructions are equivalent to this one. And then even with this, calculating this address would require an addition, because this is saying R1 plus 9. This is really what does it mean, right? So the x86 hardware will receive your move instruction at the decode unit. It will understand that you have this complex operation. It will decompose it into multiple micro instructions, and then say first calculate that address, second perform a load operation, and then do the move or the transfer between the 2 registers, which is simply just a pure RISC operation. Okay. Great. So the one we're going to use for our coverage of the instruction set is in fact the RISC, which is one example of a very old RISC instruction set, the MEPS R3000. And simply is a very simple instruction set. This is why it's good to get the concepts out of it. The important part is we're not really focusing too much on assembly as an assembly. Like it doesn't really matter this MEPS versus another, like an ARM instruction set. What matters is the philosophy. How do I design as an architect, giving a certain instruction set? How do I design my hardware? What does every instruction do? How do I really decode it? Because what I need, like as an architect, you will have the ISA manual, which is your contract, and you start thinking of designing your hardware. This is our starting point, right? So what we need to understand is if you are given an instruction set manual, how do you really get out the necessary information out of it that you need to design your hardware? And we're taking this as an example, right? You can do exactly the same exercise using other instruction sets. In reality, some of the very famous books in computer architecture that are written by Hennessy and Patterson, the ones we mentioned last week that they got the Turing Award, they have the same book exactly across different instruction sets. Like there is a book that I believe called Computer Organization and something, I forgot the actual name, for RISC-V, for ARM instruction set, for, I don't know, another instruction set, right? Because the concept remains the same. It's just a matter of the application of the examples. Good. So take this as an example, not as something that you need to really, because there are some courses where you need to write assembly code in a very certain format. I care less about this. I care more about the intuition behind what does this instruction really do, right? And if you needed to write any assembly in a midterm or a final, I will give you really what is the instruction format. You don't need to worry about it. Good. Okay, so I will stop here to give you some break before the tutorial starts. We didn't do much of the ISA, but I guess the table discussion was very critical. Again, reflect on this, and if you have questions, email me and we can talk. Thanks, and I'll see you tomorrow.